When we measure the resistance of the loads in this three-phase air core transformer, we know that the primary system is 1.5 ohms per phase, and the secondary system shown there with the label, there's two high induction coils. That front label should show 132.2 ohms, and we got meters across the back of that, and the left meter measures the left coil, and the right meter measures the one behind that, and we know that that's 132 some ohms. And we find out that when we look at the true power, in this case example of just the vibrations alone, that on the primary system we can measure the heat loss on its system by I squared R, and measure the same thing on the secondary system, and we find indeed that the secondary system has 60% more power coming out than the inputted by the primary system. When we first turn this thing on, we'll be at a 1 volt level, and then we'll turn the field on and we'll be to a 7 to 8 volt level. But on the 1 volt level we don't have any secondary engaged, but we can measure all the phase angles by noting the relative differences of voltage built on each cap system. The primary system consists of 3 1.5 ohm inductors, coiled inductors, wrapped around each other to alter their mutual inductions by each adjacent phase. And then we can see then that the ratio between the primary capacities and the secondary capacity on each measured phase pole is 272 to 1. So that means then we can compare the energy transfer of each phase accordingly. And by knowing all this above information, that's where we demonstrate time distortion. Because when we first turn it on, there is no time distortion, because we have not yet engaged the secondary loadings. And to ascertain that information and more or less try to conclusively prove that point, we're turning on now and show a 1 volt level. We don't have amperage meters, we had to work on that. According to theory, all them amperages should be balanced. These things never measure out according to theory. There's always a friggin' deviance somewhere. And that would appear to be our amperages and input voltages at this 1 volt level. Let me go look there. .27, .25, and .21. That's not a normal balance. That's not a normal balance. Only takes one wire for something to get screwed up. Now the more important data here then is these 6 meters. Right now we can make a vector diagram if we can see that bottom meter. I think everything's visible. And we can show that there's 360 degrees of time on the 6 voltage meter triangulation. Now what we're going to do then is directly go in from there. Well, first we have to turn the field on. From there, there's our real field readings. Maybe the balance came out a little better, which I cannot see by camera. Yeah, it's very balanced with the real field in there. Notice that they're all precisely around 2 amps. Yes, indeed, that's good. Now we'll be looking at the time distribution of the phases, and now we'll begin adding our secondary Earth, Sky, Xenon, Krypton, open load to the secondary potential. So that's what we're doing now. We're going to do that right away. Now we're going to hook up back coil. 7.7 volts on phase 3. Marking there, that's fairly distorted. Got the back coil hooked up. Showing 170 milliamps. Got the front coil coming in. We've got 170 milliamps on the front one, and we've got 130 on the back one. Times 7 for each of them observations. The point here is to show that now when we look at all 6 of these voltages, we're going to find that the 18-20% of the time is missing. It's got between a 290 and a 300 degree total timing circle. And then here's the amperages on that consumption. I thought I showed that. No, I didn't. No. We go look at the amperages again. The amperages have gone down probably 50%. We've got 1.1 amp phase 1, 0.8 amp on phase 2, and 1.4 amps on phase 3. The vibration has been absorbed by the secondaries. Consequent, the time distortion shown here with a 300-degree time compression, which of course we will make vector diagrams to show that and show what obtained is normally. And now we're looking here at their secondary outputs here. They're on overload. This one here, when we switch it to 10, doesn't give us a real amper. It's just over 200 milliamps. Back one is a high fluctuation of 140 milliamps. And that's what's being taken out by the secondaries. And then to end everything here, we've got to end this. There's our discharges, which are not visible in fluorescent lighting for some reason. Then finally we got to show the dump 2 coils in series and the scoping we're getting from that. Turning that on, that'll be it. That's an 80 volt signal. Right now we'll set it on 10x probe at 5x or 50 volts per division. There's a sweep actuator or whatever causes that. We'll turn that down to 2 volts per division. Correct it. know if that's very correct. That probably is correct. Since we got two different coils sending that signal. That's what our radio wave signal looks like. And the frequencies is lowered when we add more inductors in series to that coil. And we'll end here and look at our primary inputs one more time. Lord have mercy on my eyesight. I'm going to go up there and look at it again. Looks like it's 9 volts, 8.9, 9 volts, 1 amp, 1.8 amp, 1.5 amp. And the important information then, of course, is we can cite as time distortion evidence. We got 6 voltage meter extrapolation. So I think we'll end that there and pause out here with